let's just talk about bounds and constraints. Okay, so again, bounds are on our X input array, right? So we can say, you know, we really don't want X, the values of X, to walk outside of this region here, and so those are fairly simple to enforce, and most optimization algorithms will let you put in those bounds. You know, we want X to stay within this range. But then constraints are on can be on any of the outputs. So remember, let's go back to our visualization here. So our inputs, we put bounds on, or the limitations are on the bounds of these inputs. They go into this model, and then what comes out of that certainly has to at least be our objective, but there may be other outputs that come out of this as well, right? And so we can put constraints on the other outputs, you know, and say we want to minimize the objective relative to constraints on other outputs. And so that's something a little bit trickier to handle. And like Corey was saying, the SLSQP, GRG, a lot of these mainstream optimization algorithms can handle those types of constraints, and they're doing things throughout the process. They're computing gradients in those constraints, or in violation of those constraints, just like they're computing gradients of your objective function. And by the end, what they're saying is that we're going to satisfy all these constraints and minimize this objective. But during the process, we might walk out of bounds sometimes on these constraints at least. So I'm going to put just say outputs, all outputs, there can be some constraints on those. Okay, and we're going to walk through an example here, but I'd like to show you what a design space might look like for something like this. So let's say that we've got a design space here. We've got X1 here and X2 here, and then we've got contours of what the response surface looks like. And but then let's say we have a constraint. And so I'm going to put this in a different color here. Let's say that we've got some value, and we say, and if you were to, again, if you could compute the constraints throughout this whole design space at some point, you could visualize what we refer to here as a fence, okay? And so basically, and sometimes you'll see these visualized with little arrows on one side of the fence, meaning that your solution has to stay on that side of this fence. So this changes the problem a little bit, because what we've got to do now is find the point here that minimizes the objective function, but stays on that side of the fence. And that's basically what constraints are doing. They're saying you've got to stay in certain regions here and still try to minimize the objective function, right? And sometimes we have more than one constraint on there. So you know, we might have another fence that looks like this, where there's some other output that is violated if we go into this region here. And so, of course, you can see that the optimum that we're looking for would be that point right in here, if you could see this whole design space, right? But optimization algorithms, again, they're trying to find that point, but they don't know where it is a priori, and they can't visualize this whole design space, right? So optimization algorithms are trying to walk around in this region, and so let's say that we start with an initial guess over here. Well, that violates two of our constraints, right? And so one of the first things that the optimization algorithm is going to do is going to compute not only gradients with respect to the objective, but also gradients with respect to the constraints. And it's going to say, hey, if we walk in this direction over here, or, you know, I don't know what direction it's going to say, we need to walk in this direction to not only minimize the function, but also to satisfy these constraints, right? And so anyway, so some algorithms will make that a very high priority to get into what's called a feasible design space. We've initialized this in this example to a region that is not feasible, right? It's violating design constraints. This area over here, this is our feasible design space. And so usually you want to initialize your solution or provide an initial guess that is in the feasible design space over here, okay? So let's say that we initialize over here now, and what Corey was pointing out here as a difference between SLSQP and GRG is that SLSQP, as it's taking steps and computing gradients, the optimization algorithm may actually cross some of these fences, but eventually it is guaranteed to come back and satisfy those constraints, okay? Where the GRG method will not cross a fence. If you initialize it in a feasible design space, it may test some points, you know, it may try some things that violate constraints, but as it takes the next step or whatnot, it's going to try to stay inside of the fences, you know, inside of the feasible design space. And so basically we would expect GRG maybe to walk along this fence until it gets to the optimum rather than ever crossing that fence, where SLSQP will violate constraints, but guarantee that, you know, in the final solution, we're going to make sure we satisfy all of those. And there are some benefits, you know, pros and cons to both of those methods, just depending on what your design space looks like, and also the how quickly it can converge to a solution, things like that. You know, GRG might require a little bit more time because it's trying to satisfy these at every point instead of just at the end. Okay, so this is just, again, a crash course on bounds and constraints, so you're aware of what those mean and what they look like within a design space if you were able to visualize this. Okay, let's do one final exercise here, and what we're going to do is so here's another exercise. We're going to again do this in Excel. And what I'd like you to do is look at the function z equals x squared minus 2xy plus 4y squared, but subject to the constraints. And I think sometimes they say st, right? Subject to, or no, that's such that. Well, either way, we're going to add a constraint that x plus y has to remain greater than 1. Okay, so that's a constraint that we're putting on this, and let's put this into Excel and see what happens. So let's just work through this together. So here's Excel. I'm going to start a new spreadsheet here, and actually, I think what I'll do is make a copy of this guy. Create a copy. So I'm getting a lot of sheets down here that are just kind of a little messy, but okay. So here's our constraint example, and the equation that we want to look at is x squared. So I'm just going to modify this. So it's x squared minus 2xy. So minus 2 times, here's my x, times y, and then plus 4y squared plus 4. I'm just going to take that out, 4y squared. Now this a, I want to freeze the a, and I want to freeze the 2 for the b there. Okay, so this is, I think I've got my function in here correctly. All right, so there's a visualization again of the design space. I'm just leaving that plot there. But now let's actually try to visualize what the what this constraint looks like. This is x plus y. We need that to be greater than 1, right? So I'm gonna add another. I'm just gonna scale this down, and we can delete all of this. This is previous stuff. I'm just going to try to visualize what that constraint would look like. Copy that, paste it down, and this is what the constraint space would look like. And in here, it's just x plus y, right? So it's the a plus the b value, okay? And that's well, we'll move this down too. So it's actually right there. All right, so I'm going to Okay, and then this guy, I'm gonna take that space, and what I want this lower plot to do is visualize what that looks like. Okay, so this is what the constraint space looks like. You can see x plus y, and that kind of makes sense. It's this linear space, and we want x plus y to be greater than 1. So so you can see actually there's kind of this diagonal that goes through here where it's all equal to 1. And apparently this is oriented a little bit differently. I hadn't realized that, but this visualization is rotated slightly from how this matrix is set up here. But anyway, we have this space here. You can see that diagonal where it's 1. And so we basically have to stay to the bottom right of this space up here, right? So I want to stay to the bottom right here and try to minimize what's the minimum value in the bottom right of this space up here, because the bottom right is where x plus y is greater than 1. Does that make sense? Okay, so let's let Excel solve this. So I'm just going to come down here and say I've got an x and a y and a z, and I don't know what the solution is going to be. I'm just going to start with a 0, 0, and the function here is x squared. So x squared minus 2 times x times y, and I'm going to add 4 times y squared. Okay, so 0, 0 should give me 0. Let me just double check that up here in my function. If I put in a 0, 0, I get a 0. Okay. All right, so x, y, z, and then so this is my function, and then I'm going to say so up here this is my function, and then my constraint is that x plus y. So that's the x plus y, and what I need is that this value is greater than 1. Okay, so actually let me just move this over here. I'm just going to say greater than 1. Okay, so here's my function. That's the thing that I'm trying to minimize. This is my constraint here. I want that to be greater than 1. You can see that I'm violating that constraint right now. So let me initialize this at least in a place. If I make this 1, then at least I'm satisfying that constraint, right? That it's, well, greater than, I guess we'll probably do greater than or equal that to 1. Okay, so now let's let Excel solve this. So we're going to go to solver, and what we want to do is set our objective cell to this guy right there, and it can change these two cells, x and y. We're trying to minimize that objective, and subject to these constraints. So I'm going to add a constraint, and I'm going to say that this cell reference, this guy right there, has to be oh, again, it moved my menu, but it has to be greater than or equal to 1. And click OK. And so you can see that it has now added this constraint in here, that the value in that cell in C54 has to be greater than or equal to 1. And so it's going to try to satisfy that constraint. Now I could add more constraints in here if I wanted to. You can just continue to add them here. Okay, I'm going to use GRG nonlinear. Let me check my options here. Now, constraint precision does actually matter here, because it's saying I can violate this. You're going to let me violate this up to this many digits if you want, right? So you usually want to, and I think the default again is to only have 3 zeros there. I usually add a couple 0 there for the constraints. My convergence here, I want that to be more converged, and I always want to use central differencing. Okay. So now I'm going to solve that and see what it comes up with. Okay, so it's saying that here I've got an x of 0.714 and a y of 0.28. That satisfies, you can see that added together is equal to 1. And I could increase the, let me add decimals to that so that, oh wow, it really satisfied it out to a lot of digits there. And then this is my objective function. It can get down to 0.428, you know, so that's the minimum that it could find that still satisfied that constraint. Okay, any questions?